Well, up to this point in our AP Physics 2 unit on fluid mechanics, we've been dealing with what is known as fluid statics. Fluids that are in hydrostatic equilibrium, meaning that they are essentially at rest. But now we're going to be moving on to fluid dynamics, where the word dynamics specifically is referring to movement. So the flowing of these fluids. So today we're going to look specifically at flow rates and the continuity equation. So let's remind ourselves of a few limitations that we have when it comes first to fluid statics, which are also going to apply here, which is that we are only working with ideal fluids. Meaning, one, they're incompressible, so we can't compress them any smaller. We can't change the volume for a certain amount of mass. They are constant density. They're non-viscous, so no friction within the fluid or within the fluid between it and the container. And additionally, and this is particularly important here, we're only looking at laminar flow. So all the fluid is moving in the same direction at the same rate. No swirls, whirls, turbulence, or anything like that. But we need to add a further limitation this time, which is that we're typically working with what are known as contained fluids or enclosed fluids. So these are fluids in pipes, tubes, straws, etc. Occasionally, we may have an opening, but ultimately what this comes down to is that where the fluid goes in at one point, it exits some point, and it's all kind of moving in that same direction. So how do we measure the rate of fluid flow? Well, the first one is pretty simplistic, and it's going to look very, very familiar. So let's say we have some, for lack of a better word, piece of fluid at position x naught equals 0 and time t naught equals 0. Well, we can say that at some later time t, we'll say 2 seconds here, it's at a new position x equals 4 meters. So this piece of fluid right here is now located there. And if we want to know how fast it's flowing, we can just kind of rely on our old-fashioned traditional velocity equation. That v is equal to delta x over delta t, which we see here in this particular situation as 4 meters over 2 seconds, or 2 meters per second. Now we're going to change the name slightly and just say this is what we call the fluid velocity. But it still uses the same symbol we've always used, which is a lowercase v. And this is just a change in position per unit time for this given piece of fluid. It's no different than the typical velocity equation, v equals delta x over delta t, and the units are also the same, simply meters per second. But there are some other ways we want to measure how fast fluid is flowing. So let's go back to this same pipe again, but now let's say we're looking at one particular volume of fluid inside the pipe. So we'll say this is a volume of 4 meters cubed, and this is at time t naught equals 0. And at a later time, we could say this entire volume here has passed this red point. Doesn't matter what point it is, so it's all past this point and moved to this new position right past it, and that took 2 seconds for that to occur. Well, we could then say that the change in, now, okay, this is a capital V, the change in volume over the change in time would be 4 meters cubed, so this entire volume over 2 seconds, or 2 meters cubed per second. And this is known as the volume flow rate or volumetric flow rate. This is actually probably the most common way we measure fluid flow more often than not. You see it a lot with rivers, dams, pipelines, anything that's moving a lot of fluid, probably going to use a volume flow rate. Now, a couple things here. We abbreviate delta V over delta T. Now, we need to be careful. This is a capital, hopefully I can spell capital, there we go, capital V. You have to be real careful that it's not a lowercase v so we don't get confused with velocity. So capital V over delta T, but it's also often abbreviated simply as Q. So this is the volume of fluid that passes a particular point. So in this particular situation, it was this point right here per unit time, and the units are typically cubic meters per second. Now, I will say that if you see this term, we're not ever going to use it, but if you see gallons per second, which is what you might see in the United States, exact same thing. It's just an imperial unit rather than a metric unit. And let's find one final way of measuring the rate of fluid flow, which is going to be very similar to the last one, but instead of having a given volume of fluid, we're going to look at a given mass of fluid. So last time it was 4 meters cubed. Let's assume this is water. So let's say this is actually 4,000 kilograms, because water is 1,000 kilograms per cubic meter. So we have this mass. Once again, it passes a certain point in a certain amount of time. So this 4,000 kilograms passes that. So instead of having a change in volume over a change in time, we now have a change in mass with respect to time, which would be 4,000 kilograms over 2 seconds, or 2,000 kilograms per second. So this is simply known as a mass flow rate, delta M over delta T. You usually don't see another symbol for this. It's usually just that. So this is the mass of fluid that passes a particular point per unit time, almost exactly like volume flow rate, except now we're looking at mass, the unit being kilograms per second. Now, this is typical for what we call variable mass flow. So what we mean by that is that for some reason the mass is changing as the fluid flows. So that is really common for like IV units, where like IV lines where you might have like drugs or anything in the solution in it, so that could change the mass at various points. Or for instance like rockets, where rockets expel rocket fuel, but in doing so they lose some of their mass. So that's pretty typical as well. So how do we connect the different rates of fluid flow? Because we need to be able to know, well, if I have a fluid velocity, how do I get to a volume flow rate? How do I get to a mass flow rate? Etc. So let's look at this pipe again. And specifically, we look at, okay, so once again, this is kind of in terms of fluid velocity. So you have T naught and T, and move some delta X in that amount of time. But similarly, we could say, well, this piece of fluid, that is the cross-sectional area A of this pipe. So that cross-sectional area A times this delta X would give us the change in volume. So delta V is simply equal to this area times this delta X. Now the reason why we have deltas here is because this could be varying sizes of delta X. If it only went to here, that would be just this delta X, that delta V. If it goes all the way to here, that's a different delta V, different delta X. So we have the change in volume is related to the cross-sectional area times the displacement, but this all is accomplished during this time interval. We could say delta T, so let's divide both sides by delta T, but we know what this is. This is just the volume flow rate. This is the cross-sectional area, and this is simply the fluid velocity, lowercase v. So we get a combination that looks something like this, that the volume flow rate, which we can also abbreviate as Q, which is equal to delta V over delta T, is simply equal to capital A times little v. So that's connected fluid velocity and volumetric flow rate, but how exactly do we get mass flow rate in here too? Well, let's recall, first, let's go ahead and multiply every piece of this equation by the density, which we abbreviate, remember, with a rho. So we have the density times Q, density times delta V over delta T, density times AV, and reminding ourselves that the density times a volume would be a mass, so a density times a change in volume would be the same thing as a change in mass. So in fact, delta M over delta T is simply the density times the volumetric flow rate, or the density times the cross-sectional area times the fluid velocity. So let's go ahead and just piece all these together in one quick, easy space. So we have Q, which we know is equal to delta V over delta T. That is, by definition, they are the same thing, is equal to A times V, the cross-sectional area in meters squared, times the fluid velocity in meters per second. And delta M over delta T is simply rho, the density in kilograms per meters cubed, times delta V over delta T, or rho times the cross-sectional area times the fluid velocity. Now, okay, all well and good. These are pretty easy. Let's point out a couple of quick trends we need to make sure we recognize. So first off, if I have two pipes that are moving at the same fluid velocity, that every piece of fluid is moving at the same speed within them, then if I have a wider pipe compared to a narrower pipe, more volume will flow through the wider pipe than the narrower pipe. Now that's pretty common sense. Similarly, let's say you have two pipes that are exactly the same, they're flowing at the same rate, same volumetric rate, but if one of them contains a denser fluid than the other one, then the one with the denser fluid is going to move more mass per unit time than the one that is less dense. Once again, fairly common sense. Well, now that we've discussed how to describe how fluids are flowing with respect to time, let's get to our other main concept, which is this idea of what is called continuity. Now, this is a pretty simple idea, but it has a lot of important ramifications. So imagine I have some pipe here and it is closed, it's only open at the ends, for instance. Well, we know that if some mass of fluid goes in this end of the pipe, that same mass of fluid better come out the other end. So, the same mass of fluid that passes through a point in a closed pipe must pass through all other points in the pipe. For instance, it's also going to all flow through here. What goes in must come out. This is pretty obvious, that this is really just a restatement of the conservation of mass, that if I stick in 1,000 kilograms in one end of the pipe, 1,000 kilograms better come out the other end. If not, there's some sort of leak in my pipe, but since this is a closed pipe, that can't be the case. Or somehow mass is just disappearing, which is impossible. So whatever goes in must come out. But let's take this idea a step further. Let's look at this new pipe, and we can see that when the fluid is coming in, the pipe is fairly narrow, and then when we get to this point here, it widens out, and then exits the pipe when it is much, much wider. So let's go for the first step. Let's see that if we look here, we have some mass of fluids, some given delta M here, flowing past 0.1 in some given time. So we're looking kind of like a mass flow rate here. So if during a time interval delta t a certain mass of fluid passes 0.1, well, then it reasons that that same mass of fluid must pass a later point, 0.2, within the same length of time. Now, this may not seem immediately obvious, because you might be thinking, well, wait a second, why does that have to be the case? If some delta M passes this point here, then why does the same delta M have to pass this point here? So, first off, we can see that since 0.2 is a much wider cross-sectional area, that this cylinder of mass does not have to be nearly as wide or tall, however you want to think about it, here as it does here to have the same amount of mass pass that point within the same amount of time. But additionally, why does this have to occur? Well, remember, one of the important things about ideal fluids is we are only looking at laminar flow. Now, if this was not okay, well, first off, let's go back. What is laminar flow? Well, laminar flow is saying the entire fluid is moving in the same direction at the same time. If this was not laminar flow, we could have some of this mass coming through here and then looping back around, and we would then start having turbulent flow, and that's not going to happen. So we know for a fact that can't occur. Instead, what that is telling us is that since all the fluid has to be moving this way continually, well, all this mass has to pass this point, because if not, it has disappeared. It can't go backwards. So if we have a certain mass going forward to this point, from here to here, the same must go from here to here at every point in the pipe. Now, this is important because let's look back at that principle of continuity once again. So we have the same mass of fluid that passes through a point in a closed pipe must pass through all other points in the pipe. Well, we just said that for laminar flow, that means it's all going in the same direction, but let's look at another trait of ideal fluids, which is that they are incompressible. And if they're incompressible, what does that mean? Well, it means they have constant density. We can't compress them or expand them anymore. And additionally, that means if we have a certain chunk of mass, well, if it's constant density, that means we have to have a certain piece of volume. That a piece of mass must correspond to the same volume because it is incompressible. So we can actually change this idea and say that for the same piece of mass, if it's incompressible, that same mass equates to a same volume. Well, why is that significant? Well, first off, what we already basically reasoned was that delta M over delta T must be the same at every point in this pipe, because we have the same amount of mass passing this point, delta T, same thing here. This must be constant throughout the pipe. But if we take this a step further and say we're not looking at delta M, but since it's incompressible, we can consider delta V, that means the same volume of fluid must flow past every point in the pipe during a particular time interval, delta T. And if that is the case, not only is the mass flow rate the same, but the volume flow rate is the same. And it's constant for every point in the fluid. Meaning that if we look at the volume flow rate here, or Q1, and the volume flow rate here, Q2, they must be equivalent. And additionally, that means delta V over delta T at point 1 must equal delta V over delta T at point 2, since these are literally the same thing. But what does that mean practically speaking, like that's good to know, but how can that help us learn some things about a physical situation? Well, if I look here, let's say I have some change in volume and it's 4 meters cubed, passing point 1, delta t is 1 second. And I look over here, this means over here, this is also going to have to be 4 cubic meters of volume passing this point at 1 second. But if we see, the area at point 1 is much smaller than the area at point 2. And for simplicity's sake, let's say this area here is 1 meter squared, this area here is 4 meters squared. Let's make a quick note, this is definitely not to scale. Mr. Varvier did not draw this very precisely, but you get the idea, that the area here is much smaller than this area. Well, if that is the case, how can we have the same amount of volume flowing past this point as flowing past this point? Well, the volume at time 1 has to be moving faster. It has to be literally flowing at a faster rate, aka the fluid velocity is faster. Because remember, we know that delta V over delta T, we already learned, is the same thing as A times the fluid velocity. So if I look here, I have A1 equals 1 meter squared with a velocity 1 of 4 meters per second. So this is moving at 4 meters per second. But later on, if the area is area 2 and it's 4 meters squared, it must be flowing slower at 1 meter per second. And we get this main idea here. This is known as the continuity equation. Now, the first part doesn't look like much of an equation. It's really just more a statement that the volume flow rate is the same at every point in an enclosed pipe if the fluid is incompressible. That's a very important piece. This is all due to conservation of mass, but if it's incompressible, essentially that also means conservation of volume. So the volume flow rate Q1 equals Q2, delta V over delta T1 equals delta V over delta T2. Now the part that we usually think of the continuity equation is really this last point here, which is simply that means we can take it a step further and say that if there is a change in cross-sectional area in meters squared, there is also a change in fluid velocity in meters per second. So this is what this would look like in practice. We have a thinner pipe, the fluid is flowing, it gets to a wider area, the fluid literally slows down. So if I have a big cross-sectional area, I have a small fluid velocity. And then when it hits this much tinier pipe with a smaller cross-sectional area, the fluid literally speeds up and goes much faster. Now remember, this has to be for an enclosed pipe, and it must be an incompressible fluid. Alright, so when the pipe widens, the fluid slows down. When a pipe narrows, the fluid speeds up. And we've actually seen this at many points in time, even if you didn't realize it. Let's first look at this primary example, which is, you've probably seen it in a movie at some point. You'll see like people going down a river of some sort, maybe it's like some crazy rapids and the fluid's flowing really, really fast. And then when they hit this wider part in the river, they just slow down and it seems way, way more calm. And that's because there's a lot more area for it to go through, so the fluid velocity literally slows down. Now, this is not an enclosed fluid. However, the water is for the most part not going upward, so it is still moving mostly in the same direction. You get the same overall trend. Now, on the other side of things, when a pipe narrows, the fluid speeds up. You've also seen this. Now, when you take a hose and you stick like your thumb over the end of it, so you have the whole entire width of the hose, which is not very wide, but when you stick your thumb over the end of it, you've created a tinier cross-sectional area, and the fluid literally speeds up and seems to shoot out of the hose. So what are the main takeaways for this lesson on flow rates and the continuity equation? Well, first off, can you calculate rates of fluid flow and move between these different rates? So the fluid velocity, to get to the volumetric flow rate, you just multiply it by the cross-sectional area. And to get to the mass flow rate, we then multiply that by the density of the fluid. Can we utilize the concept of continuity? What must go in, must go out, and explain the origin of this idea, specifically that it just comes from the conservation of mass. Can we then utilize the continuity equation? Well, that meaning if it's incompressible, we can do A1V1 equals A2V2, where those V's are our velocities, not our volumes. And can we predict how the how the velocity of a fluid changes with respect to the size of a pipe? Wider pipe, fluid moves slower. Narrower pipe, fluid moves much faster.